So hello, my name is Keith Dillon and I'm going to be talking about efficient partitioning of partial correlation networks. So the graph partitioning problem from a really high level, we have these graphs consisting of a set of nodes and their edges. We want to partition those nodes into subsets, describing subgraphs, where within a subset we have dense internal connectivity between the nodes within the set, and between the different subsets we want to have relatively sparse, I'd say, external connectivity. And so spectral clustering is perhaps the most famous way to do this. And it can be viewed as a convex relaxation of the in-cuts, normalized cuts algorithm, which is an NP-hard problem. In the application to functional brain networks, most commonly done with fMRI data, this data is a 4D data set, or essentially have these 3D images of the entire 3D brain over time. This has a fourth dimension, which describes the variation in blood oxygenation level at each point. We call it a voxel. And so by looking at correlations between these, these time series signals at different points, we get an idea of maybe how well they're connected based on how correlated they are, right? So depending on how one breaks down these tasks, what kind of methods you use for one or the other, somehow do them both together, one might get different kinds of partitionings of the brain network, right? And some may look, say this one may look more like a realistic partitioning of the brain than others. As far as how do we decide what works well, that's a difficult problem. I've been doing some work on this, and in this recent paper, I found, interestingly, that let's get out of the way here. That if you take your data, for example, here and put it in a matrix, right? So these are the time series for different points. Each circle represents, a voxel in the brain. If you just do a raw or just a greedy clustering of these columns, so which columns are the most similar to each other, then this is it's not global optimal, but it's going to be greedy local optimal. It's going to be really hard to beat that. And this is what this blue bar show. And the R's, A is that just k-means clustering of the data method, and R are essentially little nuanced variations on spectral clustering that I applied to this data. And they were relatively good. The unexplained variance, I'm looking at the white bars first. So for a data set, so same scan I'm saying, a clustering of that data set, I'm looking at how well the centroid of a cluster, that is, say, the average over everything in the cluster, how well that describes all the signals within the given cluster. And then I average that for all the different clusters together and get a total unexplained variance metric, right? So that's essentially a scaled version of the metric which is being optimized by k-means clustering. So when you take your data and you look at how well your data was clustered, based on how well the centroids of your clusters describe it, everything within that same cluster, k-means clustering directly on the data, the matrix A, works best. However, if you look at how well it works, say how well it generalizes to some held out data or a different scan of the same person, then we find, interestingly, that spectral clustering works better, right? So most of the time spectral clustering is thought of in terms of nonlinear manifolds and these kind of things, but I don't really think that's the core important feature of spectral clustering. Or I'm sorry, yeah, spectral clustering. So the direction I'm thinking is more statistical rather than geometric. Here we go. And that is in terms of this concept from the title, which is partial correlation. So basically, when we had done spectral clustering before, I had applied it to the covariance matrix of the data. I viewed that as a weighted adjacency matrix, right? But if you have, say, indirect relationships, like I'm showing in this model here, where node K has this indirect relationship or indirect causal effect on node J, then the correlation will still be non-zero there. So you have this dense correlation that captures all, or that relates all nodes to each other, right? Whereas partial correlation, essentially you regress out all the other nodes from both of the two nodes here, and then you look at the correlation of that residual that you get left after you've done the regression. So take I and I do a regression that does the best fit to I it can with E, F, and K, subtracts that from I and keeps a residual. Does the same thing with J and then computes a simple Pearson correlation of what's left. That's the partial correlation. So it's closely related to Gaussian graphical models, which is via the precision matrix actually, which is the inverse of that covariance matrix of the data. So mathematically, essentially, if we do this regression as I'm saying here, which is slightly different than what I was saying before, but this can be mathematically shown to give the broad correlation description I gave verbally. If I take a node I and I do a regression against all of the nodes in the network, which is this one, but I ignore I, right? So I don't do a regression against itself. And then and I find the residual, right? The solution then, these regression coefficients that relate, random variables a sub k to random variable I, those regression coefficients, I can compute the partial correlation from them, right? And here's some matrix stuff I did in the paper, which I probably don't have time to get into. But the point is, this is a difficult calculation because I have to do a different regression. It's only slightly different. I have to avoid the ith column for each different node, right? So for node I avoid the ith column. Node k, I have to avoid the kth column. So there's a different regression setup each time, right? And it's, if you have a million nodes, there's a million variables in your regression problem. It can be very computationally intensive. And an alternative approach people use is via the precision matrix, and perhaps try to find a sparse inverse covariance matrix, which is the precision matrix. And that is actually computationally intensive too, and doesn't even give you the actual precision matrix. It gives you it doesn't give you the actual partial correlation values. It gives you something that's different from them, which there's some results that show if it's 0, you can assume the partial correlation is 0. If it's non-zero, you don't get the right numbers though. I'm not criticizing that direction too much. So anyway, in the paper I showed how one can efficiently essentially do that multiple regression problems, all those different solutions. I can efficiently get the solution via one pseudo-inverse matrix. Right? The inefficient way would be to form each, of the whatever it is, 1 million, say we have 1 million nodes. Regression problems find the solution each time. Well, here I can just, say via pseudo-inverse, a million of pseudo-inverses. Well, instead I can do one single pseudo-inverse. And really the key is to be able to compute one column of the partial correlation, or let's say the partial correlations between one node and all the others, for one node at a time, right? Because that's what we want with clustering, is you want to compare the partial correlations for 2 different nodes to decide if they're similar enough to go in the same cluster. And you want to average the partial correlations for a group of nodes to get the centroid for the cluster. These are 2 steps for k-means clustering. Although by no means is this k-means specific, although it is specific to maybe a square distance. But one could obviously go on and do hierarchical or some other form of clustering here. I personally don't know if it's going to be anything interesting to come out of that. So anyway, in this example with real data showing that if I compare, say, k-means clustering of data for this is a Human Connectome Project data set, versus clustering the correlations, the covariance matrix itself, and then versus clustering the partial correlations. This is for a data set that's 100,000 by 1200, which you can easily do on a computer. Then finally, the relationship to spectral clustering. So so partial correlation clustering, you can think of as clustering columns, where we're looking at the similarity between 2 columns, like with pi and pj, which is this weighting. This is an atom product. This is just a simple weighting vector which you can pre-compute, multiplied by the pseudo-inverse of the data times, and this is a scalar, and this is a vector with just a 1 at the ith location. So I want to correct out that ith term because that's removing the self-loop factor, and I'm doing some weighting, which is related to the noise, the variances. It's kind of normalization you can think of. So that's partial correlation clustering, and essentially spectral clustering can be viewed as clustering of columns in this form. So by taking out all the scalings and removing that self-loop correction, I get spectral clustering. So that's the difference. Partial correlation can be viewed as a scaled version of spectral clustering. And this plot shows that it's only a few % difference for this data set. Finally, thank you. Here's some recent papers that essentially cover my work on the spectral clustering. This paper is the extension to the partial correlation clustering.